So previously we used different equations for sigma x and sigma y. We also use equations for tau xy. With that, we derived equations for sigma 1, sigma 2, which are the maximum and minimum principal stresses, and also for maximum in plane shear stress, which was tau max in plane. Now we'll use the Mohr circle instead of those equations to get the values for these variables. So what is a Mohr circle? It's just a tool that maps or represents all possible stress transformations in a circle. So like we discussed, we'll get values for sigma 1, sigma 2, which are the maximum and minimum in plane normal stress, the tau max in plane, which is maximum in plane shear stress, and then values for theta p and theta s, which are the angles of orientation in the principal normal stress and the shear stress. Now first we'll learn about setting up the Mohr circle. Basically first we'll draw horizontal and vertical axis, wherein the horizontal will be for normal stress and the vertical will be shear stress. And one thing which we'll have to keep in mind is that in the vertical axis, the downwards quadrant will be positive for shear stress. Later we'll have to plot values for sigma and tau, and these values will be given with the problem. And then for the center or origin of the Mohr circle, we'll have to calculate the average stress. Calculating average stress in the x and y directions will give us the center of the Mohr circle. With that center and the available points, we'll draw the Mohr circle. And then the angle inside the Mohr circle will be represented by 2 theta, because we'll have a quadrant of 180 degree. And after determining the radius of the Mohr circle using geometry, using trigonometric ratios, or using Pythagoras theorem, we'll calculate the principal stresses and their respective angles. Not only that, we'll also calculate maximum shear stress and the angle it makes with the normal. Now we'll go ahead with this problem statement. So for the state of stress given, determine the following using Mohr circle, which is principal in plane stresses, maximum value of in plane shear stress, and average normal stress. And we should also figure out the orientations of each of the above. Now we'll jump into the whiteboard. So what we see in front of us is the Mohr circle. We have a graph in which we have plotted the Mohr circle. Now we'll look how we plotted this circle. Before that, we'll address the scale value. So scale value for this graph. So scale is equal to 1 cell is equal to 2 units. This means that this 1 cell will be considered as 2 units. Okay, with that we'll go into the graph. So from the setting up of Mohr circle, we understood that the downward axis, the downward vertical axis will be the positive shear stress, and this can be called as the negative shear stress. The same way the right side will be called as the positive normal stress, and the left side can be called as the negative normal stress. Now before going into the circle, we'll need to jot down all our given values. Sigma x here will be equal to 18 ksi. It's 18 ksi because the stress here is tensile stress and it's going outwards. So it's going to be plus 18 ksi. Next, sigma y will be equal to minus 12 ksi, and tau xy will be equal to 8 ksi. Again, here the shear stress value is counterclockwise, so therefore it's going to be positive. Now we have the sigma and tau axis. Next, we'll have to figure out the first point. Our first point, which is going to be sigma x comma tau xy. So for that, we have 18 comma 8 as our first point. Now keeping this point as our origin point, I'll mark this point as our origin point, and our origin point is going to be 0, 0. When we take the scale, we get 18.8 here. So this is going to be our first point. So to figure out the center point, we'll have to calculate the average stress, which is sigma average. That will be equal to sigma x plus sigma y divided by 2. And from the given values, we know that 18 plus minus 12 by 2 is equal to 3 ksi. Now this point is going to be our center point, which is 3, 0. Now this is going to be our average stress, which is 3. Now we'll call average stress as C and name this point as C. Our next step is to figure out the radius of this circle. So this is going to be our radius. So to figure out the radius, what we'll do is, okay, first we'll give these points as A and B. So to figure out the radius, we are going to use the Pythagoras theorem. So this line, which is the sigma line, is going to be CA. So we know that CA equals 2 plus 2, 4 plus 2, 6 plus 2, 8, 10, 12, 14, and then there is one unit here which is 15. So CA is going to be 15 and AB the same way is going to be 8. Therefore, our radius, which is R is equal to root of 15 square plus 8 square. Therefore, R is equal to 17. Now, R value is the value of tau xy or the value of maximum in plane shear stress or tau MIP. So, I'm going to give tau MIP as plus 17 KSI. So, with that, sigma P1 is equal to C plus R. So, C plus R is C plus the radius. So, for us, this value will be C and C plus R is equal to 3 plus 17, which is equal to 20 KSI. And sigma P2 is equal to C minus R. This region is C minus R, wherein we know that this small region is C and this whole line is our radius. So we'll just call this as DE. So DE is going to be R C minus R. 3 minus 17. And that is equal to minus 14 KSI. So now that we've got values for sigma 1, which is equal to 20 KSI, and sigma 2, which is equal to minus 14 KSI, and we know the values of these lines CA, AB, and the radius of the circle, which is 15, 8, and 17. Our next step is to figure out the orientation angle, which is theta P and theta S. So theta P is the orientation angle when it comes to the normal stress or the principal stress, and theta S is the orientation angle when it comes to maximum in plane shear stress. So for theta P, we have the equation tan 2 theta P, which is equal to opposite by adjacent. So it's going to be 8 by 15, and 2 theta P is equal to tan inverse of 8 by 15, and theta P is equal to 14 degree, or from this equation only 2 theta p is equal to 28.1 degree. The same way, from equations we know that the value of 2 theta s is equal to 90 minus 2 theta p1. So this is from geometry. So we have taken this from these angles wherein the summation of this angle is going to be 90 degree, and 90 minus 2 theta p will get 2 theta s. So we know the value of 2 theta p, which is 28.1. So 2 theta s is going to be 61.9 degree, and theta s is going to be 31 degree. So here we've got theta p as positive, and our shear stress is going to be a negative orientation, which is minus 31 degree. So with that, we have found out values of theta 1, theta 2. In the previous board, we also figured out the value of tau MIP, which was the radius of the circle, which is 17 ksi. And then later we also figured out the values for theta p, which is 14 degree, and theta s, which is minus 31 degree. With that, we'll move on to the next concept, which is absolute maximum shear stress. Now, the strength of any ductile material depends on that material's ability in resisting shear stresses, making this a very essential part for us to calculate the absolute maximum shear stress in that material system which is under loading. Now, we can do this using Mohr's circle, and we'll be focusing more on the volume elements in order to do this. So what we see on the screen is a 3D element. So this 3D element has 3 directions, x, y, and z. And then we have made them into 3 parts of 2D elements. The first one is xy plane, the second one is the zx plane, and the third one is the yz plane. So now we'll move on to the whiteboard to see on few important terminologies that we'll be using for calculating the principal stresses on volume elements. Now in the first element, which is the xy element, we know that x has a stress of 450 psi. So we'll give 450 psi here. And in the same way, the next is going to be our y element, for which the stress is 250 psi. So if we keep plotting these, again for the x element, the stress is 450, and for z, it's going to be 150, which is inwards. We'll have to keep this in mind. The z direction stress is inwards. So 150, and for y, it's 250. So here we can say that our sigma maximum, which is the maximum stress, is 450 psi, and our sigma minimum is the z direction stress, which is 150, and we know that it's an inward stress, so it's negative 150 psi, and the intermediate stress is, for this problem, it's going to be 250 psi. So basically our maximum stress is sigma x, minimum stress is sigma z, and intermediate stress is sigma y. Also, to find out the maximum shear stress or maximum absolute shear stress, we'll use the formula sigma x or sigma max minus sigma minimum divided by 2, where this equation, which is sigma max minus sigma minimum, will be the diameter of the circle which we plot in the Mohr's diagram. as for the Mohr circle, first we'll give our coordinates, which is the tau coordinate and the sigma coordinate. So this will be sigma and this will be tau. And as for the circles, we'll have to first plot the points. The first point will be our maximum point, which is sigma max, and that will be 450. And next we'll plot the minimum point, the sigma minimum, and that will be minus 150. And as for the circle, this is our bigger circle. Now the circle which we have plotted here is for the zx plane. So the zx plane will have the biggest circle where we have 150 and 450, which is minus 150 and 450 as our stress values. So let us call this the zx circle. The next point which we'll have to take care is the intermediate point, which is 250. So we'll plot that point somewhere here. This will be our intermediate point. And as for the intermediate point, this will be the smaller circle, and this will be the intermediate circle. Now, this circle is governed by minus 150 and 250. So therefore, this circle is the Mohr circle given for the plane YZ. And the same way, this circle is governed by the points 250 and 450. Therefore, this circle is governed by the XY plane. Now, as for the plot of tau max ABS, it's going to be the diameter divided by 2, which is basically the radius of the circle. And here, for us, sigma max is going to be 450 and sigma minimum is going to be 150. Therefore, our value for sigma max minus sigma minimum divided by 2 is going to be 450 minus of 150 divided by 2, which is equal to 300 psi. Now, we can mark 300 somewhere here. And finally, this point will be our tau max or maximum shear stress point. The maximum point here which we marked, which is 450 for this problem, is also called as the Mohr's dot. Now with that we can move on to the next problem. Now given here is a thin walled pressure vessel and it contains liquefied propane under the pressure of 210 megapascal and it's transported at 100 degree Fahrenheit. We have the inner radius which is 6.16 inches and wall thickness as 0.11 inches. Here we have to determine the principal stresses and overall maximum shear stress at any point on the surface outside and any point on the inside surface. Now all this while the elements which we were working on were only solid pressure vessels. Here because we are given thin walled pressure vessel, we have a little bit change in the stress equation we will be using. Now moving on to the whiteboard. So in this given problem, we are supposed to work with thin walled surfaces. Now for thin walled surfaces, the pressure formula changes. It's not the same as we saw earlier. So our sigma 1, one of the principal stresses would be P/R/I by T, wherein P is the pressure exerted on the vessel and Ri is the inner radius and T is the thickness. So we have the thickness and radius here. So with that we'll be working this problem. In the same way, sigma 2 will be equal to PR, which is pressure into the internal radius divided by 2T, which is exactly half of the first stress. So here after substituting the values, we'll get sigma 1 is equal to 11,817 megapascal. And same way, sigma 2 will be approximately 5909 megapascal. Now, considering a 3D element, but the first thing we have to find is any point on the surface. On the surface is outside surface, which is the circumferential surface. So, considering any 3D element in the circumferential surface, so we'll consider sigma P1, sigma P2 as the values which we found. But when it comes to the third value, which is sigma 3, we can say that it's going to be 0. So basically, sigma 1 is going to be 11,817 and sigma 2, which is the perpendicular value for sigma 1, is going to be 5909. But because this is the outer surface, the third sigma value is going to be 0 because there is no pressure exerted on the outer surface. Pressure is exerted only on the inner surface, and that too on the inwards direction because it's a pressure exerted by the liquid. So basically sigma 3 is 0. For better understanding, I'll write external here, which is the first question which we are addressing. So this is the first question which we are addressing. Now, if we take the sigma maximum value, it's going to be 11,817 and sigma minimum value is going to be 0 and sigma intermediate value is going to be 5909. And as for the Mohr circle, so first we'll draw the coordinates and we'll give it tau and sigma. So our first value, which is minimum value, is going to be 0 and the maximum value is going to be 11,817. So we can draw a circle for these two values. Our next step is to figure out the tau max value. So for tau max, we know the formula, which is sigma max minus sigma minimum divided by 2. And we know that the minimum value of sigma is 0. So 11,817 divided by 2 is going to give us 5909. So 5909 is the same as our sigma intermediate value. So for this problem, the intermediate stress will be our maximum shear stress, going to be our tau max. With that, we'll go to solving the second statement, which is any point on the inside surface. So as I said earlier, pressure due to a liquid is always inwards, and we know that this is inside the pressure vessel. So we'll write inside for better understanding, and we are solving the second statement. And because there is an inside pressure or inside stress, we can call it sigma x, which is equal to minus 210 MPa. You can call this sigma x or one of the stresses, which is sigma 1. So we'll call this sigma 1. Again, sigma 2 is going to be 5909 and sigma 3 is going to be 11,817 MPa. We got these because we have already solved for this in the previous point. The only new stress which we have got here is the sigma 1, which is minus 210 MPa. And when we take for minimum and maximum and intermediate stresses, we'll get that sigma maximum is going to be 11,817 as always. Sigma minimum is going to be minus 210 MPa, which is the pressure inside the vessel that is exerted by the liquid. And then sigma intermediate is going to be 5909 megapascal. And if we have to mark these values in this 3D element, then we'll quickly erase these two arrows, because we know that inside the vessel, the pressure exerted by the liquid is inwards. So this will be inwards and it's 210. And the outwards pressure would be the same, 11,879, 5909. Now, as for tau max value, we know tau max is equal to sigma max minus sigma minimum by 2, which is equal to 11,817 plus 210 divided by 2, and we'll get tau max value as 6013.5. With that, if we have to work with our Mohr circle, so this is going to be our vertical coordinate line and this is going to be our horizontal coordinate line. So let this point be our minimum point, which is minus 210, and this point be our maximum point, which is 11,817, also called as the Mohr's dot. And if we have to draw a circle, it's going to be the biggest circle. Now we know the value for tau max and we also know the value for the intermediate point. We'll quickly plot the intermediate point, which is 5909, and our tau max will be 6013.5. So this will be our tau max value. With that, we can plot the rest of the circles. The first circle, which will be governed inside minus 210 and 5909, which is this. And the second circle will be from 5909 to 11,817. Now this will be our Mohr's plot. And with that, we come to the end of this session. So in this week, we learnt about stresses in certain directions which can have completely different stress components acting on them when an applied load results in the rotation of their element. We also came across calculations for the same using principal plane equations, and we did the calculation for both normal stress and shear stress. So we defined the calculations in two different methods. One was the principal plane equation. The second was the Mohr circle. We also did problems relating to it. And we learnt about the concept of absolute maximum shear stress. And finally, we ended this session by solving few problems about absolute maximum shear stress. See you with another concept in the next week. Thank you.